Okay, well, we'll make a start there. I've only had a few more people just recently join, so hopefully that's everyone. Again, thanks a lot for joining, everyone. And I probably say this every week, but it's nice to see some new faces on as well. And every week we seem to be getting more and more new faces, which is really nice to see. But again, as I always mention, it's really nice to see, people that have completed the course, people that have even helped to write the course there. We've got Andrew joining us as well. So, that it's a nice mixture of people on this call. And again, I really want to start promoting this this community side of things. It's not just me teaching this. Again, like we're just all putting our own spin on it. So the more people we can get in, whatever, area they're coming from, whatever knowledge level they're coming from, again, it's amazing to see such a wealth of experience and knowledge in here. So again, really appreciate everyone's time tonight. So yeah, sorry, I didn't even introduce the module then. So it's module 4 of Awakening, which is velocity pipe sizing. And again, it's sort of a build up from what we did last week. So last week, if you wasn't on the call, we did module 3, which was mass flow rate. Again, that was the foundation for this. We're then moving on to velocity pipe sizing. And if you're not fully aware of what comes next, module 5 is around the pressure loss or the resistances of pipe sizing. So again, pipe sizing really is in 3 parts. It's the mass flow rate first, which again opens up a wide range of things, which we'll discuss again today. Velocity pipe sizing is the next part of it. And then obviously you've got your pressure loss. And then once you combine them all together, you'll be pipe sizing in the real world. So again, this one, I'm not going to lie to people, and I've mentioned it to Alex before, I'm sort of going to contradict what I usually do by simplifying everything, whereas this is quite heavy on the maths, and I'm just going to lay it out there. Like if you've completed this module, you're probably fully aware of this already, but this is heavy on the maths, and it's heavy on the maths for a good reason. It's taking you back literally. I remember doing this in like year 9, year 10 in maths class. Like there's a lot of that kind of stuff involved. Hopefully we can make it a little bit more relatable in a way. Well, we are going to make it more relatable. Maybe that comes with a bit of more of an enjoyment or a bit of more of an interest in it as well. So again, I'm just going to lay it out there. It is heavy on the maths. A lot of people do say this is the module that they struggle on the most. And when I've looked at the data, I can see where people usually either drop out or stay on it for a longer period. And this module is one of them. So again, like, don't be put off by that. If you get through this, well done, congratulations. And again, like, it is a tough module, but again, it's so rewarding once you get through it, as I'm sure you're aware if you've already done it. Again, I've introduced myself every week. I'm not going to do the long spiel. One thing I did want to mention on this one, just sort of because I've introduced the maths element to it. I've found, during, if you don't know, I was an engineer for like 10 years, and I went into teaching. One thing I found when I was teaching is, applying the maths to something relevant and something real, like it sticks better in my opinion. And I've noticed that with so many of the students I've taught as well. Like I had a lot of students who they would be on a plumbing and heating course. They still had to get the maths and English because they hadn't got the grades in school for whatever reason. They were literally designing systems. I'd teach them all this kind of stuff. They'd be pipe sizing, they'd be designing systems, really into it. And then they'd still go to the maths class. And then I'd get a report from the maths teacher saying they're not interested. They're not even, attempting what I'm showing them. And it was sort of like, this doesn't make sense because I'm literally teaching them maths and, we're just applying it to pipes and radiators and whatever we're doing. And then they go to the maths class, and because they weren't relating it to anything real, they weren't interested at all. And and I think I'm coming from that background as well, where when I was in school, I wasn't too interested in the maths. And I'm not saying that like everyone has to come from that background, because they definitely don't. But what I'm sort of saying is that if you did struggle in school and you wasn't interested in this kind of stuff, like it doesn't hold you back doing this. Once you start applying it to your everyday real life practices, it does stick, and it becomes a lot more interesting because, you're actually doing something with it. You're actually making it relevant. And I think, that's something that we sort of need to understand. And so what I'm trying to say is don't be put off by, the heavy maths in this, because, you're more than capable, 100%. So there's my little introduction. Last week's recap. So it was module 3 and it was mass flow rate. Again, if you wasn't in the session, I put the recording of that session in quite a few places as well. So I wanted to show the wider community what we were doing, because again, I think this is so important, these sessions. So it's in all the Facebook groups. It's also on LinkedIn as well. I wanted to share one on there just to see, if we could get more people interested in the course as well. So hence that. So if you did miss it, I'd probably grab hold of that recording if you were interested, if you don't know what we're talking about with this. But I will be going over this again because it becomes relevant in what we're actually doing today as well. So again, that is the mass flow rate triangle, or the volumetric flow rate triangle. Again, you've got power on the top, you've got mass flow rate at bottom left there, and you've got specific heat capacity multiplied by delta T in the bottom right. There's a hand in there for a reason. Again, sorry for the people that have already been over this, but basically whichever one you're trying to find, I usually just teach people just to cover it up. So, if for instance, we're trying to find out what the flow rate is, we would cover that up, and then you've got power over SHC multiplied by delta T. If you're trying to find out what power is, you cover that one up, and because the mass flow rate, SHC and delta T are all next to each other, it's just a multiply. So again, that's how the triangle works. Same as the Ohm's law triangle, same as some of the triangles I'm going to show you today as well. Again, everything has a relationship with each other. So if you follow that logic, you won't go far wrong today either. Again, the agenda, and it's only for the people that haven't been on these sessions. So again, apologies for the people that have been on every week. Slides are just a guide for the conversation. Take me away from the slides. It's perfectly fine. Please don't worry about that. And as part of that, please get involved. The hand button, where is it? It's literally a hand. If you've got a question, press that down at the bottom. It'll say that you want to say something, and I will literally cut myself off mid-sentence and let you talk. So, if it's a question, if it's a point, please get involved. If it goes a little bit too far, I might just rein it in a little bit. But again, please don't worry about getting involved. I'd love people to put their spin on stuff. And then final bit, again, massively important with this one. The aim is to understand it, not just to pass the test. And I know that there's people joining today because they've been on this module for a while and they want to pass the test, which is brilliant. And, hopefully this does help you. But the main aim of this is to understand what's actually going on behind this. And towards the end of this session, I'll start to sort of go into how you use apps to do this kind of stuff as well, but which is great. But you also have to understand the theory and where this is coming from, where the apps are coming from. Basically, this is vitally important. You can't just walk in with an app and start thinking you can pipe size, because you'll get stuck at some point. So the aim is to understand, not just pass the test. Brilliant. Okay, so the first slide, just to introduce this, because again, some people have got stuck on this, and you can see why. It's basically the difference between flow rate and velocity. So again, we did flow rate last week. And in short, or in the simplified version, flow rate is just how much fluid moves in a certain time. And again, if you think about that as a sentence, that's just basically how much energy are we moving at that point in time. So we basically measure that in liters per second. Again, as we went through last week, that bottom left hand corner of the triangle that we kept showing, that was all about flow rate. It was measured in liters per second. So it's about how much fluid, which is why it's in brackets, is moving in a certain time. Velocity is different than that. Velocity is how far that fluid travels in a certain time. So again, we measure that now in meters per second because we're actually measuring how far it goes. And you can see at the bottom there, the calculation for that velocity is distance divided by time. So again, if you think about that for other practices, like that's just indicating speed in a way. And I know it's not fully speed, but it's sort of an introduction to what speed is, like how far is it moving at what point in time? So, miles per hour, things like that, just sort of related to that kind of stuff. It's literally, the speed that the water is moving, which is obviously different than flow rate, which is how much of that fluid we're actually moving at one point in time. Okay, so that's the difference, just to give people a bit of a heads up on that. So here's my first question, and it's an open question, so please get involved. Why is understanding velocity important in heating system design? So just to introduce it to everybody else, anyone want to jump in of why understanding velocity is important in a heating system design? Anyone want to jump in there? Alex, I think you use the first one.
So we got obviously velocity. If it's too fast, and you create noise and turbulence in the pipes. Brilliant.
Awesome. Nice. And I'm going to push you a little bit further there, Alex. How much would you say is too fast?
Is it 1.5 meters a second?
Nice. Brilliant. Nice. Brilliant. So as part of the guidance that we offer, we say 1.5. So again, there's a couple of numbers here thrown on the screen for you. So, we've got the max there down at the bottom, as Alex rightly said, the guidance is 1.5 meters per second. And again, it is only guidance. If you do go a little bit above that for a short period, you're probably going to be fine. But again, it's just for guidance purposes, 1.5 meters per second, we're indicating as the maximum for there. The nominal or the perfect would be 0.9 meters per second. And again, these numbers are vitally important just to understand what's actually going on here, what kind of area you're trying to get into. And then a minimum, and I say minimum, and you can probably see in the brackets as I read through, we indicate that a minimum of 0.5 meters per second. But again, you'll realize this through the course that a lot of times Heat Geek are saying that that's hardly ever an issue in a domestic setting, and again, probably because of the size of the systems and things like that. And that there is a case for air, sediment, or all this kind of stuff if the velocity is too low, so the water's not moving as quickly as what it should do. So again, the minimum guidance is 0.5 meters per second, but again, in a domestic setting, maybe not too much of an issue. But key one there is the 1.5 meters per second. So when we're designing a heating system, so why is it important? We need to understand what velocity is and what some of the issues it can cause. And again, there's a couple of images I've just thrown on the screen there just for reference. And you might have come across this before. Well, you probably have come across this before in the real world. If let's take the lever valve, for instance, on this one. If you turn a lever valve so it's almost shut off and that water's flowing through, you can hear this water flying through. And again, it's that velocity basically that's causing that noise. So again, there's things with that. There's the erosion of the pipework and all that kind of stuff comes into it as well. And again, we cover this in the course, and it's all throughout there. There's a lot of things around this, but I just sort of wanted to introduce this of why do we need to know this? Why do we need to understand velocity? Why is it important in the real world? Because again, we've got these issues. So 1.5 maximum as a guidance, nominal 0.9, and then the minimum is 0.5. Again, if you go below that, maybe not too much of an issue in a domestic setting there. Brilliant. And then again, more importance of velocity for the real world is, obviously this is pipe sizing. This is why we're going into this now. This is, why it's important. And pipe sizing is based on 3 areas. It's the flow rate required, which again, we did last week. So again, that's why we do our heat loss calculations first. We need to know how much basically energy we need to put into a certain place, and that's why flow rate is so important with this. Next point now is velocity, which is obviously this module, which we're going to cover. And then next week's module, as I mentioned, is the pressure drop then. And that's what pipe sizing comes down to. And I alluded to it last week. And again, I sort of, when I watched it back, I was like, I feel like I was sort of saying that I knew nothing before. And I probably didn't, to be honest. But, like during my own learnings and stuff, it was all just based on rules of thumb, like no more than 3 rads. No more than 3 rads or 15 mil. And it's like, that's just completely wrong. And, this is how you actually pipe size. You don't just use rules of thumb of we're doing this, without actually understanding why. So again, this is what this is all built up to. You'll be able to pipe size once you understand these 3 things. Okay, so diving into this now properly. Again, if you need to make notes, please do. I'll leave obviously the images on for longer as I'm talking around the screen. If you want to get involved, please get involved. So this triangle that I've called the velocity triangle, basically, this is a triangle that we're going to be using a lot during this module, and it's important to understand these numbers and all these bits of data and why we need to use them. And it works the exact same way as the mass flow rate triangle, works the exact same way as your Ohm's law triangle, all that kind of stuff. So at the top there, we've got volumetric flow rate, and one key thing not to get stuck on here is how it's measured. So we're measuring this as meters cubed per second. And again, you can probably understand why when you look at the other 2 that are here. We want to keep it in meters just for ease. You can go a little bit crazy with this and you can expand on it if you wanted to, but for ease, we want to keep everything in meters, basically. So, we've got meters per second of volumetric flow rate. I'll show you how to convert all this in a minute anyway, don't worry. So that's at the top. Bottom left-hand corner there, we've got area. Really important when you're doing this is that it's the internal area of the pipe. It is not the it's not the total area of the pipe. So again, when we get into this, you'll start thinking about wall thickness and all that kind of stuff. And then you can maybe start to apply that to plastic pipe and all that kind of thing as well. It's not just relating just to copper pipe. So again, it's the internal area of the pipe. But again, be careful with the units that we're using. It's in meters. Okay, so we're not in millimeters here, so we might need to do some, conversions. or meters squared, sorry. And then bottom right-hand corner is velocity. And again, that's what this whole unit is centered around. Velocity, as we've already mentioned, we're measuring it in meters per second there. So again, really important triangle, one to write down, one to, you know, try and get onto your brain eventually. But again, you need this wrote down whilst you're going through these assessments, this module. Okay, so rather than just talking about it, we're just going to basically put this into some questions, and hopefully, you know, through the examples, people can pick this up and where we're going with this. So I've just thrown this question out here. So basically, what's the volumetric flow rate of water in meters cubed per second flowing at 0.8 meters per second through a pipe with an internal area of 0.002 meters squared? One thing I will say before we start, do not get worried by all these decimal points. And I think that's where people are sort of get a bit scared straight away when they start seeing all this. Okay, just plug the numbers in, basically. Don't worry about decimal points or anything like this at this stage. Just plug them numbers in. So anyone want to tell me what the calculation would actually be for this? Where would we even start? Stevie, you were the first one up there, mate. Do you want to jump in?
So obviously times the area by the velocity. So get
nice,
the answer for that.
Brilliant, brilliant. Do we need to do any conversions, Stevie, or can we just put that straight into this triangle with the units we've been given on this question?
Yeah, you can put it straight in this triangle.
Okay. Awesome, brilliant, mate. Awesome.
Triangle, yeah.
Nice, mate. Awesome. So again, everything on that question is already in meters. We do not need to convert anything. It's already in the same SI units that we're using in that triangle. Okay, so again, we're asking for a volumetric flow rate in meters cubed per second. It's telling us we've got a velocity of 0.8 meters per second, and we've got an area of 0.002 meters per second. So again, just stick them straight into the triangle on this question as an introduction. And once you put that into there, again, not too important to get the answer again, and like in the test, obviously it is. The most important thing on this is understanding where the numbers come from. Hopefully everyone gets that. If you don't, again, just, you know, stick your hand up. You know, as Stevie said, cover that one up. You've got area multiplied by velocity. That's going to tell you what your flow rate is in meters cubed per second there. So it's 0.0016 meters cubed per second. Okay. But again, like, that was, you know, straightforward once you understand the triangle, once you've sorted out your SI units. Making, I've called it like the next step up now. So, you know, let's progress that a little bit. What about now in liters per second? What is the flow rate of water flowing at 0.8 meters per second through a pipe with an internal area of 0.002? So if you're not fully aware of this, the numbers for the velocity and the area are the exact same as what was previous. Obviously, the top part of it has changed. So now we're asking it for in liters per second. Anyone have any idea how we convert meters cubed per second into liters per second and want to have a go at this or explain this to people? Stevie is first up again, mate.
Right, mate. So times up by 1,000 will take you for meters cubed to litre per second.
Awesome, mate. Spot on again, mate.
0.16 litres per second.
Brilliant, mate. Nice, I love it. Give us the answer as well. Nice. So perfect. First thing to do is work out what we've done previously. Okay, so again, use the triangle. Yeah, and then all we're going to do then is again convert to liters per second. So as Stevie said, multiply by 1,000. So you've now got 0.16 liters per second. Okay, and again, like understanding why, all this kind of stuff. 1 cubic meter holds 1,000 liters of water. So that's where that number comes from. Again, that's as simple as we can make this, and that's as simple as we need to go with this. 1 cubic meter holds 1,000 liters of water. Okay, so again, you just got to convert by multiplying by 1,000. If you go in the other way, obviously divide by 1,000. There's lots of questions in this module relating around this, and all it is just understanding that. So liters per second to meters cubed per second, all the other way around. Again, the key number here is 1,000. And again, if you're not fully aware of that, I'd probably just write that down somewhere, just how you're going to convert this. Okay, nice. So that was the top part of the triangle done. If we look at that there, so we've got, you know, meters cubed per second, and we've boxed that off. Again, convert it to liters per second if you need to at the very end. Next bit is area. This is where it gets a little bit more intense in a way, and a little bit more, in depth on this one. So area is obviously the bottom left-hand corner now of the triangle. I'll put the triangle on most of these slides just so you can keep referring to it. So it's bottom left there. It's in meters squared as well. So again, just try and remember it's in meters. So to find area, basically the first thing we've got to be aware of is that when we're typically buying pipe, it's basically told us in, full diameter basically, or the external diameter. So, your 15mm pipe, sorry, if someone just else wants to join, sorry, your 15mm pipe, is not actually 15mm as an internal diameter usually, okay? And again, it's something that we just need to be aware of. It's just something that we need to apply to our calculations. So to find the internal diameter of a pipe, as it says on the screen there, it's our outer diameter, or our full diameter, if you want to think about it like that, minus 2 times the wall thickness, okay? And again, like if you look at the image on the right, the diameter is literally straight across the circle, if you think about it like that. The reason that we're doing 2 times, because if you start at one end of it, you're going to go through a wall, then you've got the internal pipe, then you come into another wall. That's where that 2 comes from. It's understanding the why, okay? So take your full outer diameter, basically. So if it was 15 mil, it would be 15 mil. Then 2 times the wall thickness, minus that from it, and then you're going to get your internal diameter. So as I put an example there for this one, we've got 15mm copper pipe, and the wall thickness of that in this example, and for most, to be honest, it is 0.7 millimeters, okay? So even though it's 15mm pipe, you've actually got a 0.7 wall thickness on that. So if we put these numbers into that calculation, we're just going to basically do 15, which is our outer diameter or our full diameter, minus 2 times the wall thickness. So because the wall thickness is 0.7, multiply that by 2, we've got 1.4 obviously, and then minus that from our 15mm, that's 13.6. Again, if anybody gets stuck whilst I'm talking, because I'm very conscious, we don't want to lose anyone here, just please put your hand up, please be honest and say, I do not understand what you're talking about. We can keep going over it, or somebody else can jump in and explain this. So again, nice and straightforward. I think just to start off with step 1, you need to have this wrote down somewhere. This is crucial. This is in so many of these questions on this assessment, or this module. Okay, so 15mm copper pipe, your actual internal diameter is 13.6 millimeters. Next part now, again, don't get lost. Because we're working the flow rate in meters cubed per second, and we want to keep everything in meters, basically we need to now convert our internal diameter, which was just calculated, into meters. And again, going from millimeters to meters, we're basically just going to divide by 1,000. So you've got 13.6 millimeters divided by 1,000. We've now got 0.0136 meters. Okay, so for our internal diameter, in this example, 0.0136. And again, for that reason, keep everything at meters, just so we can plug it into that triangle. If you want to convert it to millimeters, you can do so at the end, or we've got another example where we can, do something a little bit different as we move forward. Just a bit of a note on copper versus plastic as well. And this is, if I put the note at the bottom, because I think it's vitally important, this is only for the pipe work. I'm not bringing in the inserts for the fittings and stuff, which is obviously going to drag this down even further. So pipe size, or OD, outer diameter for 10mm pipe. For plastic, it's actually only 7 millimeters, and then this is just typical. This is not for every single one. So again, do your research on whatever pipe work you're using. You've got 7 millimeters plastic internal diameter on 10 mil plastic pipe work. Copper, it drops down to 8 millimeters. So again, you've got an extra millimeter if you're using copper 10 mil. 15mm pipe. On plastic, you've got 12 millimeters there, copper 13.6. I feel like I'm just reading off the screen here. Sorry, it's really boring. 22, you've got 18 on plastic, and you've got 20.4 on copper. All I'm trying to emphasize is that wall thickness on plastic. Again, with the barrier pipe as well, it basically, it's going to reduce that pipe work down, the internal diameter down pretty far. Well, obviously a lot more than what the copper is. Key point on this, though, is that note at the bottom. Once you start putting the fittings on there with your inserts in and stuff, that internal diameter is going to get reduced down even further as well. So, something to be very, very conscious of when you're designing systems, and when you're selecting what material you use as well. Again, don't want to be telling people what to do and what not to do, but just be fully aware of what is there, and what we are actually, using here. So, yeah, take that as you will. Okay, so once we're finding the area, and again, I'll just because I did like a little bit of a sidetrack there, the final part we got to there was we'd found the internal diameter of the pipe. Okay, so step one, we found the internal diameter of the pipe. We converted it into meters. We were at 0.0136. The next thing we're going to do now to find the area is, finding the area of a circle, and we go back to when we was, 12, 13, whatever, maybe even younger than that. Basically finding the area of a circle, pi r squared. Okay, and I think people have probably heard that before. Well, you definitely heard that before. You definitely would have done this when you were younger. Probably never used it ever since. You're going to start using it again now. Nice and straightforward. Like literally, all you got to remember is that terminology that you've probably heard, for the last however long. So to find the area of the circle, it's our internal. Again, vitally important to remember that the area of the internal part of that pipework is pi r squared, and obviously, the radius is the internal as well. Everything we're doing is the internal. So step one to find the radius. Basically, all you got to do is take your diameter of 0.136, and you're going to divide that by 2. So the images at the top are sort of trying to jog your memory of what radius is. Okay, so divide that by 2, and then you've got that there, taking our initial one of 0.136, our diameter, divide that by 2 is 0.068. Okay, so that's our radius there. Okay, the first thing you need to do, and probably the most important thing, is to put in the key, which I probably should have made a little bit more obvious. You must square the radius first when you're doing this calculation. Okay, so that's why I've done radius first. You're then going to square the radius. Okay, so it's 0.068 squared, and you get that number there. Okay, I'm not going to read all the numbers out. It's going to get really boring. Everyone's going to switch off. Okay, so that's what we have there. And in step 3 then is you've got your radius squared now of your internal diameter, and now all you're going to do is basically multiply that by pi, and then again that is now our area, or our internal area of our pipework at that point there. Okay, and key point, it's in meters squared, it's not in millimeters at this stage. Okay, hopefully everyone's okay with that. Probably, once you go through the course again, once you revisit this again, I would write this down. Again, if you can't remember every single step on this, I'll probably just write this down. I will just go back one stage. First thing is find your internal diameter. You find your internal diameter by step 1 there. Again, make sure that is wrote down. Take the internal diameter, divide it by 2 to get your radius, square it to get your radius squared for your pi r squared, and then multiply it by your pi, obviously then, and then again that gives you your area of your internal bit of your pipework there. Okay. So again, now we're sort of moving on to the velocity. So hopefully everyone's okay so far. We've covered the top part, we've covered the bottom left, and we're now in the bottom right part of the triangle now, which is the velocity side of things, and trying to relate it to real world stuff. Okay, you will need to come across this. You will need to have an idea of what's going on with this when you come into these systems. So in this example, we've got section B, which is the 2 radiators, which is the pipework feeding the 2 radiators on the left hand side there. It's currently fed from a 22mm copper pipe with a 0.9 millimeter wall thickness of that copper pipe. Okay, so we're trying to work out what velocity would be experienced if the system was filled with water, the flow temperature was 44, and the return was 39. Okay, and this is similar to some of the questions you will be asked. I might have even gone a bit further on this one, just to try and make it a little bit more relevant to everything else we've just literally talked about, and last week as well, just to give you a clue. So this question hopefully should build all this stuff together that we've been through. So first thing, again, you're in the real world, you've done your heat loss calculations, you've come out that you need to send 5 kilowatts down that pipe work, that section B pipe work. You've seen that it's 22mm pipe, you've done your research, you found that 22mm copper pipe has a wall thickness of 0.9 millimeters. And now you're trying to work out what velocity would be experienced if the system was filled with water. Again, think back to last week if you were on the call of why that's important. The flow temperature at that one point in time was 44 degrees and the return was 39. Okay, so I'll just put that back on there. So anyone want to dive in with what would be the first thing to answer this question? What would you need to do to start off with? And the question's still on the screen if you wasn't listening to my boring voice then. I'll give you Stephen.
Work out the area of the pipe started?
You would do that.
I'm trying to work this here in my head backwards. Obviously, you've got your DT times the 4.2.
Nice. Okay. Nice.
Yeah, flow rate.
I like it. So mass flow rate. Nice. That's what we're after, mate. First thing you ever need to find. Again, think back to that one of the first slides I put on. Like when you're doing pipe sizing, what's the first thing we need to do?
Yeah.
It's mass flow rate. Yeah. You can't do anything if you don't.
Side, so yeah, get your mass flow rate. Obviously, and then divided by 1,000. That'll be the top section of your triangle. And then obviously work at the area of your pipe to divide by. Will give you your answer in meters per second.
Awesome, mate. Brilliant, brilliant. I like it. Awesome. So, as Stevie just said, find the flow rate. Okay, we need to work out mass flow rate. Step 1, 5 kilowatts. Okay, it's divided by 21. Anybody else want to dive in? Because Stevie just explained it perfectly. Anyone else want to explain why I'm using 21 in this calculation? Where does that number come from in terms of this question? Oh, no worries. So, Alex?
So specific heat capacity of water and delta T of 5.
Nice. Awesome. Brilliant. So again, for the people that weren't on last week, thanks a lot for that, Alex. Your specific heat capacity of water, we're going to use 4.2 for this. Okay, so 4.2 multiplied by our delta T. Our delta T is just difference in temperature. And the flow temperature, as we said there, is 44. Our return temperature is 39. So difference in temperature of 5 degrees or 5 Kelvin. So it's literally 4.2 times by 5. And again, if you want to design the optimum system, so you design into a delta T of 5, you just need to remember that number 21, because 4.2 times 5 is 21. Bottom right-hand section of this triangle is going to be 21. So again, we've covered up because we're trying to find out what the mass flow rate is in liters per second in this example. So basically, it's 5 divided by 21, that gives you 0.24 liters per second. And then step 2, as Stevie rightly said, we now need to convert that liters per second into meters cubed per second, because that's what we need to use to actually find our velocity, to put it into that velocity triangle. I've just made that, that's not what it's called, but I've just called it that. So again, like we need to basically then convert that. So step 2, we're going to go the other way from what we've shown before. We're actually going to do divide now, because we're now converting from liters per second into meters cubed per second. So instead of multiplying it, we're actually going to divide now. So we've got 0.24 liters per second divided by 1,000. We've got 0.00024 meters cubed per second. And straight away, we've got that top part of that triangle sorted there. So again, looking at that question originally, there's a lot going on there. You've just got to find out what your mass flow rate is. Start with flow rate. Flow rate is king, you know, as they all say. That's the most important part. Work that out first, and then everything else will fall into place. You've just got to remember these little conversion factors that we've got. So get it into meters, or meters cubed per second, as it says there. That's how we do it. So divide by 1,000 there. Okay, next part of it now. So as we've sort of alluded to already, and as Stevie just went and just explained this whole thing, which was brilliant. I love that. Like the next part now, we've got to work out that area. Okay, so we've got the top part of the triangle sorted. We need to work out this area. Once you've got 2 parts of this triangle, you can find that third part, and obviously the third part that's left is the velocity. Okay, so as you rightly said, we need to calculate the internal diameter of the pipe to start off with. And again, it's the exact same thing that we talked about before. We're basically taking the outer diameter, or the full diameter, whatever you want to call it, minus 2 times the wall thickness. So in our example now, it was 22 millimeter pipe that we've seen here, as the question at the top shows. If you know, it's conscious that there's going to be a lot of talking, a lot of writing on this, so just keep referring to that question. 22 millimeter copper pipe with a 0.9 millimeter wall thickness. 0.9 multiplied by 2, you got your 1.8 there, minus that from the 22. Your internal diameter pipe here is 20.2 millimeters. Again, we need everything in meters for this part of the calculation. So convert it now into meters. So you've got 0.0202 in this case here. So again, same thing that we've done all the way through. Don't be worried by the decimal points. Just keep doing it as you're doing it. And I think quite a lot of people slip up here, and you know that you're halfway through, you've done a huge calculation, like you've done amazingly, and then you just put the decimal point in the wrong place, and it all falls apart. If you've not noticed this on the new courses, like it's all from a question bank. So you've got literally, I think there's like 8 different versions of a question, which can be frustrating. And I know it's frustrating. I just want to sort of raise this point now because I've had so many messages of people saying, I got it wrong, I've got to do it all again. You've got to do it all again for the reason is that once you do this over and over again, and I know what it's like, it's so frustrating, but it sticks. It helps it to stick. And I promise you, it does help you, as frustrating as it is. You know, if you've not chucked the tablet through the window, this is going to help you, I promise. And it's that whole point of it's different than every other qualification you are going to gain in this industry, where it's multiple choice, it's out of 4, you get it wrong twice, then you get a verbal question, which is the exact same question again, and you've already got it wrong twice, and the guy's literally, or the persons are literally telling you what to tick. That's not what we're doing here. That's why it's question bank. That's why it's different, and you have to do it all again because it sticks and it makes you understand, not just pass. So again, a little bit of a rant, sorry, I'll come back to this. Convert to meters, we've got 0.202 meters. The animation's messed up, sorry. Step 5, again, we're just doing the same thing that we've already been through previously with a 15mm pipe. So we've got the internal diameter. We can now find the radius because we've already got the diameter. So half that diameter gives us the radius. So our diameter was 0.202 divided by 2 gives us 0.0101. There's our radius. Next part, again, the calculations on top, if you forgot, literally square that radius, okay, and that gives us that answer there. And then finally, we're going to multiply that by pi. And again, key point, we're in meters here, so it's 0.00032. And it's just that calculation. We're just putting them numbers into that calculation. There is a lot of calculations to remember. Just make sure they're wrote down when you're doing the actual test on this one. Okay, so final part now is we've basically calculated on the left-hand side, we calculated the flow rate or the volumetric flow rate, so the meters cubed per second. We did that, as you can see there. That was the screen that we've seen before. So again, we got our liters per second. We then converted it to meters cubed per second. We had that wrote down somewhere. So we got 0.00024 meters cubed per second. That's that top bit of the triangle done. The right-hand side of the screen is our area, okay? So again, we found our diameter, we then calculated our radius from that, we squared the radius, and then we multiplied it by pi r squared, and that gives us 0.00032. So we've got the value for the bottom left, and we've got the value for the top. Again, I'm not going to bore everyone by going through what we do next and covering stuff up. It's literally going to be that divided by that, and that gives us 0.5 meters per second. Again, key thing, everything's in meters, so our answer comes out in meters per second there. So we've got 0.5 meters per second. If you're following the guidance, that will be perfectly fine to use, okay? It wouldn't be optimal, but once you get into the real world and you start doing this, you realize there's not many things that are optimal, okay? And again, like, you've just got to find out, will it work? Can I get it into my calculations? Can I make it work in some situations as well? And again, like, this is the whole point of this. Get it into that ballpark, do your calculations and say whether it can be used or not. No rules of thumb, none of this. You can't use 10 mil on a heat pump system, none of that crap. Like, you just do your calculations, work it out. Okay, so 0.5 meters per second is our answer to that. Again, quite a long-winded question, but you're just taking all them little bits that you've just learned and you're just plugging it into this triangle. That's all you're doing there. We'll work on that. And then this part now, and I think, like, you know, I'm not going to go through this because I was very conscious of time, and I did start putting the slides in, and suddenly all the slides got to about 35 slides, and I was like, you know, I think people are already sort of going to be switching off at this point. So all I'm going to do is basically tell you where to go if you want to work out this one. When you're on the module, there's literally a link that says, this is what it says. Literally, I've just copied and pasted this. So another way to do this would be to use this formula that basically combines all of this. Okay, so you can literally choose a pipe size or an internal diameter by combining all of them calculations together. That is what the formula looks like. And again, it's putting it into millimeters initially for you there, if you look at it that way. So you've got 2000, you've got your square root because you're doing the inverse of it. And again, like, you'll see this, and there's a picture really strange that I've just put a picture of like Peony on here, but he does a video on YouTube. I think he did it because he was doing a uni, I don't know, he was doing something at uni basically, and he you know, it had this light bulb moment of how we can combine all this kind of stuff that we've been learning at Heat Geek with what we've been doing. And again, other people were doing this as well. Mike just did the video on it, explained it, I think, perfectly. You know, like if you watch that video, he really does, as you can see on what's happening on screen there, he breaks it down in individual steps of why he's doing this. And again, that's so important. It's not just this is what it is, it's why we're doing this. So again, it's on the YouTube channel, on the Heat Geek's YouTube channel. If you go onto the module, you've got a link on there as well, which takes you to it. But Mike explains it perfectly. So again, I definitely check that out if you were interested in combining this whole formula together and finding out a pipe size based on, you know, your basically your mass flow rate, if you want to look at it like that. Yeah, definitely worth checking out there. And then what I sort of wanted to do is sort of go back to what I sort of alluded to at the start of this as well, that, you know, this module is heavy on the maths, and to be completely honest with you, everything we just covered there will get you through that module. And I know it's sort of like we only did like 2 questions, but little bits of that are individual questions in this module. So again, the heavy maths and all that kind of stuff is literally, it's not that heavy once you break it down like we've just done. Just literally write down them key steps. How do you find internal diameter? How do you find the area of a circle? And then how do you convert, you know, your liters per second to meters cubed per second? Once you've got them 3 things wrote down, to be honest, everything else just falls into place. So yes, it's tougher than the other modules that you've done previously, in my opinion, on the math side of things. But again, just write them down. What I sort of wanted to do then, which is sort of what I'm wanting to do with all of these, you know, sessions, is sort of related to real world. And again, why are we doing this? Why are we teaching this kind of stuff? And, you know, it's so important to understand why, and then how to apply it into real life practices. And I wanted to put this in, and I sort of mentioned it to Alex before we started, in that, you know, in that new book I wrote, I sort of put like, nobody works out the cross-sectional area of a pipe. And then, you know, in real world, and, you know, I sort of made a joke about it, but we don't, like, you know, and fair enough, like, you know, some people do, which is fair enough, and I love that. But, you know, if you're on the job and you need to work it out in the split second, you took the floor up and it's something that you didn't expect, you're like, okay, what do I do now? Typically, me personally, I wouldn't get a piece of paper out and start doing all that. I'd be like, okay, what do I do to quickly think, can I use that pipe or can I not use that pipe? And there is quick ways of doing it. There's apps, there's cheat sheets, all this kind of stuff. So I just sort of wanted to show people what is out there. But again, if you looked at this piece of, you know, this graph, the key point here is that you'd have no idea what you was looking at if you hadn't already done this calculations. This is what Heat Geek is about. It's understanding the calculations. Okay, how to apply it into real world practices. So this chart is literally a cheat sheet chart. This is on the optimizing course. If you've not already done the optimizing course, there's a few more modules about to be added to optimizing as well. So again, we're constantly updating this kind of stuff. So there's a few more modules coming out. This one is one of them. And this is literally, it's a cheat sheet. It's based on Delta T5. And, you know, as you can see, that the first column there, we've got power, we've got the flow rate already calculated for you. You lot won't need that because you literally know how you would get to Delta T5 if you're using water, and please don't use glycol. So again, you would already know that side of things. But for the people that don't, it's a cheat sheet to say, if you've done your heat loss calculations and you've got a 4 kilowatt heat loss, then, you know, you don't even need to really look at that. You know, you can just go straight across, which again, I'm sort of on the fence of, you know, do we do that or not? But, you know, there's our flow rate. Then you've got your pipe sizes there. So this is copper pipe sizes. You've got 8, 10, 15, 22, all the common ones. And what you'll see underneath each pipe size, you've got PD and you've got VEL. So PD is pressure drop, and pressure drop, again, I've wanted to stay away from pressure drop this week. I wanted just to do it as its own module next week. So again, I will show this again next week, and we will go through this just specifically on pressure drop. But the VEL is obviously velocity, what we've been talking about this week. Again, so if you're looking at this, like green is optimal, that is, you know, perfect. But in the real world, what you'll find is, as I've mentioned, like, you know, you could save time, you could save the customer money, you could save, you know, disruption in a way by using something that wasn't optimal, as long as it fits into your calculations. And as long as it fit into your calculations, you've actually calculated it, you've not just guessed or just tried it to see if it would work, then it's perfectly fine. You know, do the calculations. So if it's orange, do the calculations. And again, it's saying that, you know, it's not optimal, but it'll probably work as long as it's fit into your calculations. So, you know, if I took the floorboards up, I knew I'd done my calculations, and I knew that going to that section of pipework, let's say, was, I don't know, 5 kilowatts. and it was 15mm pipe. I would find there like 5 kilowatts. I'd go across, I find 15mm pipe. It's telling me it's 1.67 meters per second on terms of velocity. It's a bit higher than that 1.5. Again, like, you know, this is where they can make that engineering decision. It's not coming out at, you know, 3 meters per second or something crazy. Make the calculation based on your knowledge and your experience on that. And again, like you've got your pressure drop there, and we'll talk about pressure drop next week, but you know, it's got a high pressure drop compared to 22mm pipe. It's got a higher pressure drop than compared to 28mm pipe. It's all relative, basically. And again, like seeing it in a chart like this, it's just so easy just to refer to. But again, we'll go through this in a lot more detail next week. One thing I wanted to point out is there's that it's 76 here, but there's that 0.75. It took us 10 minutes to talk through and work out. You know, you literally say, well, it's 5 kilowatts. If you remember that load going down the left-hand side, and then we did all them calculations to find out. If you looked at this chart and you went to 5 kilowatts, you go across and it's 22 mil, I'd say it was 0.75 or 76 in this case of meters per second. There's your velocity straight away. How much time that saved you. But again, so important to understand where that come from. Even quicker way, if you've not got, you know, this printed out or anything to hand, is the one on the right. And again, I don't know if I'm allowed to, you know, do this, but let's do it. That's a free app. It's High Tools by IMI. Again, if you never come across this, I would recommend downloading this onto your phone. This was literally just a screenshot taken from my phone at 2 o'clock today. So many things you can do with this app for free. It's actually like, it's amazing that it is actually free. So again, in this case, you can see at the top there where it's LS, so liters per second. All I've got to do is I've got to put in, you know, what that is. And again, it's just that knowledge of, okay, what's my delta T, what's my heat specific heat capacity, and then what's my kilowatt. Once you've got them three things, and you can work this out of, okay, I want delta T of 5, I've got 5 kilowatt load, 5 divided by 21 is 0.24 liters per second. Put that in at the top, tell it what the material is. So we've got copper in this instance. And then if you go down the pipe sizes, then it tells you, first bit is your pressure drop, which again, we'll talk about, but the next bit then is your velocity in meters per second. Again, there's that 0.75. You've done that calculation in all them different steps and remembered all that stuff. I literally went onto my phone, did 5 divided by 21, okay, 0.24, put that in, bang, straight away. If it's 22 mil, it's 0.75 velocity. These apps are becoming, you know, like such a big part of our lives in terms of system design. But again, we need to understand how we even get to this point. If you give someone that app and said, okay, use that, they'd be like, what number do I put in LS? And then you say, oh, you know, you'd have no idea. You'd have to understand where these numbers come from. So again, key thing there is in the real world, you know, use this kind of stuff. And again, have an understanding, have a respect for where these numbers have come from, and obviously double check them as well, because some of these can be completely wrong. I think this might be the final one, actually. We've just gone through a bit too quick here, but connection points, again, for the real world of when you are doing your pipe sizing and things like that, you could get a little bit smarter in the way that we're doing certain things. And again, there's obviously in the real world, there's a lot more things to think about. You know, this may not be possible in some cases, but I just sort of wanted to mention it while we're here. So the one on the left, let's say that, you know, if you're going out to a property, and, you know, typical property where, you know, the whole main section of the pipework is 22, let's say, for the instance, in this case, and it was branching off in whatever. So your main section is 22. If you had a heat load, as it says really small, sorry, at the bottom of the heat pump of 11 kilowatts, and you were trying to connect onto 22 millimeters pipework, you might do your calculations and work out that, you know, maybe your resistance is too high for, you know, your pump, or maybe your velocity is going to be crazy high. If that's the case and you're just connecting straight onto that pipework, again, you might say, okay, I need to repipe all that in 28 millimeters pipe. Again, disruption increases, cost increases, and time increases. If you're a little bit smarter in a way, and you could do this, and I know it's easy for me to say sat here, on the right-hand side there, if you thought about how can I split the load, how can I split that 11 kilowatts load, if you know, went in basically in the center, you know, even doesn't have to be the center as long as you've calculated it. If I went bang in the center of that load, and let's say this house was perfectly like laid out nice and easy for me, where, you know, half was 5.5 kilowatts, let's say, you could keep them 2 bits of 22 millimeters pipe that you've just basically split in half there, rather than repiping everything, just for the fact of where you've connected that pipe work in. Because if you think about this, like, you're not sending 11 kilowatts down to all them 4 rooms anymore. You're only sending 5.5 to them 2 and 5.5 to them 2. It's only the primary pipe work that, you know, you're typically going to have to do anyway in a heat pump that you're going to connect in. So the point where you connect into a system is also vitally important with pipe sizing. And again, it's all that it's just design, and you can say design is the most important thing, and the reason for that is because it's just planning out your installation, basically, of calculating it. Why am I doing this? What is the the best for that customer? What is the best for the installer? And then this could be that in some cases. So again, it's just having a little bit of nous in a way of like, okay, if I do that into that middle there, I can split this load. I don't need to convert all that 22 million pipes to 28 anymore. I can I can leave it as it is. So that's that. So again, we've got a time here. Any questions, anything that anyone wants to mention or put their spin on or anything like that? Well, we've got a bit of time. Please, please do shout up. We'll go with Colin. Do you want to jump in there, mate? You're on mute, sorry.
What if the velocity is too low? Can it be too low if the pipe size is originally too big on a retrofit? Good question.
So the Heat Geek guidance is that typically in a domestic property, it's not an issue in too many cases. I think like what you may realise is you do have sediment build up in if it is too low, because obviously that bit of dirt, a bit of sludge is not flying around the pipework anymore in these bits of low velocity. It will stick, but again, you would get that in any case where it's it's low velocity. That's why your radiators collect the sludge in the bottom and things like that. That's why if you had an air jack in there, that's why they used to block up and things. So typically in a domestic setting, Heat Geek's guidance is that bigger is better. And so if it is too low, typically in a domestic setting, it's not going to be an issue. If you're doing commercial work, then definitely calculate, and it can be too low. But in a domestic setting, the guidance is, for most cases, that you'll be perfectly fine as long as you clean the system out and you cleared the air in it originally. You should have no issues with it being too low, below that, 0.5. But again, yeah, it's a good question, mate. I like it.
Thank you.
Andrew, do you want to jump in there? You're on mute as well. Sorry, Andrew. So it's just a microphone button at the bottom. I can't see it, so you can type it into the comments and I'll read it out if you want to. Okay. Anybody else whilst Andrew is typing that one out? Stevie?
Hi, mate. I was just wondering, see, next week for pressure loss, do you think you'd be able to touch on KV values and valve authority? I know it's not actually in the module, but
yes, 100%, mate.
Actually, I watched a few of Andrew's YouTube videos. That was really helpful. If we could just touch on it, it would be really handy.
100%, definitely, mate. Definitely.
Cheers.
Awesome. Okay. So Andrew's comment, I love this. So he says, I think the long formula is incorrect. Nice. And Andrew, can you come off mute? Is there any chance you can't? Oh no way. We're gonna miss out on the legend speaking here. So Andrew, if you could send me an email or
I've worked it out.
There you go, you're on. Go on.
I had to go into permissions. So
nice. I'll put the formula back on.
I could be wrong. I could be wrong here, but I think the formula after the divide, so the 1,000 times delta T, etc., that should be in brackets. And I don't understand why, because normally when you've got division and multiplication, you can just put them in one line.
Yes.
But I just checked it and double checked it, and it does have an effect if you don't have the brackets. So I think the brackets are important, but it needs to be double checked. But
okay,
I've always carried out with the brackets. I use this formula all the time.
Yeah.
I don't do the process you've taught. I just know I just look up the power needed for a circuit, pick it through that formula, look at the diameter it gives me, and if my pipe's near enough, it's near enough.
Yeah.
So it's a really, really quick, easy way of doing it. But I've always got it in the brackets in that second section. And you'll get the wrong answer if you don't have the brackets there, I think, but maybe you'd like to check.
Brilliant. I will double check that. Thanks, Andrew.
No problem.
I'll have a look at that. Thank you. Appreciate it. Awesome. Anybody else got anything to add or any questions?
How do you mute it again?
Just the microphone button at the bottom. Brilliant. So, and again, I just want to say thanks to everyone. Like, great input from everyone here. We've got Colin from the Netherlands here joining us as well. So nice to have him in as well. And as I say, that the amount of people on and the difference in the level of experience and what they've added here is, it's been amazing. So again, thanks a lot for this. And again, next week's one will be on the pressure drop. And Stevie, I will definitely be incorporating KV values and valve authority and all that kind of stuff, because again, it was a great point and something that we do need to incorporate into this. Again, Andrew's videos are on YouTube. If you've not seen Andrew Miller's videos on there, check them out as well, because there's some great knowledge on that. So next course is on Thursday the 31st of July. So next Thursday, 5 to 6 again. If you want to look at the verification side of things, so to work under Heat Geek's umbrella and want to understand about the apps and all that kind of stuff, the next webinar for that is on the 6th of August. Again, it'll be myself doing that with Sean, the community manager, and we can talk you through and answer any questions and all that kind of thing on that too. But again, just want to say thanks to everyone for your time this week. And again, we're finishing bang on time again, which is nice. So yeah, have a good one. I'll hopefully see you all next week.
Cheers, Lewis. Thanks.
Cheers, Lewis. Thank you.
Cheers.
That's the fastest an hour has gone in a while.
Oh, nice.
Well done. Cheers.
Cheers.